Hello, this is the last part of the Networks Optimization Models lecture, which will include minimum spanning tree and the shortest route problem. We've already talked about transportation problem and the assignment problem. I will not discuss the maximum flow problem. Minimal spanning tree MST problem is a problem where you need to find the shortest distance that connects all the nodes of a network. Let's imagine that those nodes are cities and the links are the proposed highways to connect these cities, and I want to find the shortest total connection that will connect all these cities directly or indirectly. That is called the minimum spanning tree problem. The algorithm to solve the MST problem is pretty straightforward. It's a grid algorithm where you start at any node in the network and then you find the shortest connection to this node to any other node. And then you include that in your solution. So you have now two connected nodes. And now for these two nodes, you will find the third node that is the shortest connection to either one of them, and so on. So mathematically, you start with a set n that includes all the nodes. Initially, none of them are connected, and then you select the connected node set C0 at iteration 0. It's empty, and this is C0 bar, which is the complementary of set connected, which is initially all the nodes are still not connected. And that's how you initialize the algorithm. Step 1, then you select any node in general, then C1 becomes node I, and let's say it's node 1, and then C bar 1 would be all other nodes except I, because you already selected I. And now the next node you include to set C2 now would be a node J that has the closest connection, direct connection from I to J, and so on. So showing it with an example is probably the best, and it's very straightforward. These are 6 nodes, cable connections to the Midwest TV cable company, and they need to put cables to connect all these 6 nodes, and these can be 6 cities. So what is the most economical network? That means the smallest or shortest distance of cables or length of cables that connect all these cities. And as I said earlier, you start at any other node. In this particular example, they started at node 1, so C1 becomes 1, and C1 bar all other nodes, which is 2, 3, 4, 5, 6. So we have the first node is selected actually. Nothing is connected yet. The next node to select would be the shortest connection, direct connection to any other node. So you see that node 1 is already connected to nodes 2, nodes 3, node 4, and node 5. That's it. And the connections are, the distance or the length of the connections are 1, 9, 5, 7. The smallest is 1, and thus we now connect nodes 1 and 2 together, making one island, which is now set C2 becomes those 2 nodes, as we're going to see in the next slide. So this is still showing the process that I just described in the previous slide, that C1 is connected to all these 4 nodes, and these are the connection distances. The smallest is 1, which will be. Once we have chosen to connect nodes 1 and 2, so set C2 becomes nodes 1 and 2, and set C2 bar all other nodes. Now, here's the trick in the algorithm, or not the trick, but this is something to be careful about, is the next step is I need to connect or select the node with the smallest distance to any other node in this C2 bar island. So it could be from node 1 or it could be from node 2, and that's why it's not showing the connections within C bar 2. I don't care how they're connected, but basically you have the connection from this island C2 to the other island C2 bar through these various connections, regardless of what are the particular nodes. So in this case, you can see the connections are 3, 6, 4, 9, 5, and 7, and the smallest is 3, and thus node 3 will be selected. So now C3 will have nodes 1, 2, and 3, 1, 2, and 5, I'm sorry, because the distance is 3, but the node is 5, as we will see in the next slide. So now C3 is 1, 2, 5, C3 bar is all other nodes, that is 3, 4, 6. Again, what is the closest or the shortest connection between those two islands, regardless of what nodes they connect, but they have to cross the two islands. The shortest connection that crosses the two islands would be this connection that with a distance of 4 that connects node 2 to 4. So that means now set C4, in the next slide we're going to see that set C4 will be 1, 2, 4, 5. And so on. Now you will be writing down the sequence of connections so that you keep track of what nodes were connected at what iteration. Even though it's not important to know that, what's important is actually to put the connection at the end between those nodes, which will constitute collectively the minimum spanning tree. So the next node here to connect from the two islands of C4 and C bar 4 would be this shortest connection 3 between 4 and 6, and thus C5 will be 1, 2, 4, 5, 6, and C bar 5 will be node 3. And finally, you're going to see that those connections are from the two islands C5 and C bar 5. The shortest is 6, and this is the connection between node 2 and node 3, which will be added to the set. Apparently 5 can be reached from two different connections. 1 and 3 is 5, 4 and 3 is 5. So it doesn't matter which one you select, you can select either one arbitrarily, and then this will also give you a solution. So there is an alternative optimal solution in this case. One time you include the connection 1, 5 and not 4, 3, and then the other time you include the connection 3, 4, of course not 1, 3. The second problem we're going to look at in this lecture is the shortest route problem, SRP. It is different than the minimum spanning tree problem. In the minimum spanning tree problem, you need to connect all the nodes. All the nodes need to be connected within the shortest or the smallest connecting arcs. However, in the shortest route problem, we do not need to connect all the nodes. We need to go from a start node to an end node using the shortest distance. So you may obviously will not pass through all the nodes, you will pass through a subset of the nodes that will take you from start to finish. The lengths, I mean, you can imagine that you're going from city A to city B, passing through various other cities, but you want to take the shortest distance from city A to city B. Here's an example of the shortest route problem, and consider this 6-node network, and the problem is you need to get from node 1 to node 6 in the shortest possible way. So one way of going there is 1, 2, 4, and then 6, and that's the cost of this route would be 4 plus 2 is 6 plus 3 is 9. Another route will be 1, 3, 5, and 6, and the cost of this route would be 6 plus 2 is 8 plus 7 is 15. So you can see you can solve this problem through exhaustive search, but basically you need to figure out all possible routes from one node to the next, which is not an easy problem for networks that have hundreds or thousands of these nodes. The way we solve this using an algorithm called Dijkstra's algorithm, which you're going to see in the next few slides. Here's the LP formulation. Obviously, these problems, all of these problems, the shortest route problem or the MST, are all LPs, linear programs that can be solved, that can be formulated as an LP and solved using the simplex method. But obviously, because of their special structure, we learned simpler approaches or algorithms to solve these problems. Here's the LP formulation for the shortest route problem, whereCij's are the distances between node I and node j, and Xij is a decision variable where Xij equal 1 if that route is taken, and Xij equal to 0 if the connection between node I and node j is not considered, and so on with few bunch of constraints. Examples of the shortest route problem include obviously project scheduling, equipment replacement, and traffic routing, obviously. Obviously, you can also use the Jensen solver to add into Excel Jensen solver to solve both the shortest route problem and the minimum spanning tree problems. And I advise you that you try at least one problem for the shortest route to be solved with Jensen software. In the previous example, the shortest route from the beginning node to any other node is displayed on this network. For example, the shortest route to node 3 is 6, which was actually distance from 1 to 3. But the shortest route to node 4 here is also 6, which is probably the route from 1 to and then 4. But anyway, this is the shortest route, 9 from node 1 to node 6. What is this slide is showing that the Dijkstra's algorithm that we will show in the next slide allows us to find the shortest route not only from the beginning to the end node, but also the shortest routes from the beginning to any other nodes. So that's what you need to keep in mind once we do the solution using the Dijkstra's algorithm. Dijkstra's algorithm is a labeling algorithm, and it works as follows. Let's consider this example. We have this 5-node network, and we need to go from node 1 to node 5 from start till the end, node 5, using the shortest route, finding this route using Dijkstra's algorithm. We start Dijkstra's algorithm by assigning a permanent label to the start node. So the node 1 is the start node. We assign a permanent label to it, and that label is 0. That means the distance traveled to this node is 0. We haven't moved an inch yet, and we're coming from nowhere, so it's a dash, and this is a permanent. We always start this. You can write this actually label next to the node directly, so you can write 0, comma, coming from nowhere, close, and I put an asterisk or a star next to it, signifying that it is a permanent node. So that's step 0. Step 1 is place a label next to all nodes that are not labeled yet, that can be reached from all permanently labeled nodes. In this case, there's a single permanently labeled node, which is node 1, and nodes 2 and 3 can be reached from node 1, and thus I see in this table that there are 2 labels defined for nodes 2 and 3, and the labels are as follows. Label next to node 2 or for node 2 becomes 0, which is it's coming from this distance, 0 traveled, it's coming from 1, comma 1. So 0 plus 100, the distance, so 0 already traveled to node 1 plus the distance from node 1 to node 2 is 100, and comma it's coming from 1. Thus the label becomes 0 plus 100 is 100, comma 1, and that's the label that should be placed next to node 2. And again, as I said, I can write the nodes next to I can write the labels next to the nodes, and this way I can write here 100, comma 1, close it. And I do not put an asterisk yet because it's not permanently labeled yet. It's a temporary label. The next node that can be reached from node 1 is node 3. The label next to it would be 0, which is the cost here. 0 plus 30 is 30, and this is coming from comma from 1. Now at each iteration step I will choose one from all the temporary labeled nodes to be a permanent label. In this case I have this is temporary and this is temporary. One of them will be made permanent, and the one that will be made permanent is the one with the shortest distance. And in this case I will compare the 100 to the 30, and 30 is the minimum, so thus 30 is made, node 3 is made permanent, so I put an asterisk or a star next to it, and then I will erase actually all other temporary labels that I have calculated. And I will repeat this process again for building a similar table like this, but now I have 2 permanent labels, as I will see in the next slide. Here we see, yes, node 1 and node 3 are permanent now, so I will have to calculate temporary labels for all the nodes that can be reached from those 2 nodes. From node 1 I can reach node 2, the same thing. So node 1 I will rewrite the label next to node 2, which is 0 plus 100 comma 1, which is 100 comma 1. I can write this next to the node, as I said here, no problem, or I can just use the table by itself. I cannot reach any other nodes from node 1 because node 3 is already permanent. It can be reached from node 1, but node 3 is already permanent, so I don't have to recalculate this label. Once it's permanent, it will not be recalculated. And now I can reach nodes 4 and 5 from node 3, which is made permanent. And the labels next to node 4 would be, what's the label on node 3? Label on node 3 is 30 comma 1, so 30 plus the 10 here is 40, comma, coming from where? Coming from 3. And the label on node 5 is 30 plus 60 is 90, coming from also node 3. And and also I have obviously the label on node 2, which I didn't write next to the node, but I can read it from here. It's 101. I will select those 3 are temporary labels, and I will select one of them to be permanent, and the one that has the shortest distance and or the smallest number in the first entry, which will be 100 versus 40 versus 90. And 40 is the smallest, so 40 is made permanent, so I put an asterisk next to it, and then I will erase those labels, other temporary labels. So I have now 3 permanent labels, the one for the initial one for node 1, and one for node 3, and one now for node 4. Those are permanent labels. Mind you, the algorithm does not stop even if by chance we selected node 5 which is the destination node, the end node, to have the permanent label instead of node 4. I will have to continue. The algorithm, Dijkstra's algorithm, ends only when all nodes on the network will have permanent labels. Okay. You can see here what I mentioned in the previous slide, that node 4 was selected to have the permanent label, in addition to the originally node 1 and 3 that had the permanent labels. Now I have to recalculate the labels for nodes 2 and 5, because those are the only 2 left without permanent labels. And here Node 2 can be reached from node 1, which is permanent, and it can be reached from node 4, which is permanent. So I would calculate both labels for node 2 starting from two different permanent labels. So the label for node 2 starting from node 1 would be the same one, 100, 1, and also it will be, so, or coming from 4 now instead of 1, it will be, what was the label on node 4? The label on node 4 is 40. So 40 plus this 15, it will be 55, comma, coming from node 4. So right there, I will actually remove the longer label, which is 100, 1, and only stick with 55, 4 as a temporary label yet, and that's why you see it here 55, 4, but you don't see the 100, 1. Okay, and if it was 50, 1 or 55, 4, then I will take the 50, 1 instead. But here 55 is the smaller. But still, again, this is not permanent yet. I have to recalculate the node. I have to recalculate the label for node 5, again coming from two different places, from 3 and from 4 going to node 5. So the label of for node 5 coming from 3 would be, what's the label on node 3? It's 30 plus 60 is 90, and that's coming from node 3, or coming from node 4 will be, what's the label on node 4? The label on node 4 is 40 plus 50 is also 90. Notice here that both have 90, so either one of them can be selected, but you know, if one of them has 100 and the other is 90, then obviously I will stick with the 90, the smaller one. So here it doesn't matter which one you keep. I'm gonna keep let's say 90 coming from 4, and then I will compare this 55 and 4 and 90, 4. So 55 is the smaller anyway, so this will go, and this one will be made permanent in this iteration. Okay, so in the next slide you're going to see that now we made the node 2 is permanent, and we're the only node left without permanent labels. As I said, the only node without label now is node 5, and the label next to node 5 would be coming from 3 or coming from 4. Either ways, it's 90, 3 or 90, 4. So either one of them is fine. Okay, so this is what I just said. The two labels are 90, 3 or 90, 4. Both are fine, and the problem actually ends. You select by selecting either one of these. So how do we read the answers? How do we read the result? If I'm traveling from, here's the write-up here is for the shortest distance from shortest route from node 1 to node 2, and then I can read that as the shortest route is 55. I read the number directly. Okay, 55. That's the shortest distance from node 1 to node 2, and the path is coming from 4. So 2 coming from 4. So I go to 4, and I don't need to read the distance anymore. I just need to read the predecessor, and this is coming from 3. So I go to 3, and this is coming from 1. So I go to 1. So the path is 1, 3, 4, 2. 1, 3, 4, 1, 3, 4, 2. And that's the shortest path from 1 to 2. Now if I want to do the same thing to figure out the path from 1 to 5, the shortest path from 1 to 5, then I can read the distance is 90. That's the final answer. But the path is either coming from 3 or coming from 4. As I said, we select 1. There's an alternative route. Both are optimal. But let's say I selected the one coming from 3. So 90 is the distance. The path is 5 coming from 3. So I go to 3. I read 1. Then 3 coming from 1. So the path is 1, 3, 5. That's the shortest route from 1 to 5. Obviously, this is a simple network, and you may be able to figure that out by inspection. However, in large networks, as I said, where it involves, let's say, thousands and tens of thousands of nodes, it's not a simple matter to inspect the network visually and figure it out without the algorithm. And this is particularly useful, like Google uses this algorithm when they find travel distances between two cities for driving purposes. Okay, we will look at two different applications of the shortest route problem. One application is called the equipment replacement problem, and the other application is called the most reliable route problem. Starting with this equipment replacement problem, the problem says that there's a rental company that would like to develop a replacement plan for its car fleet for the next 4 years. And you're going to think of these as future dates, okay? So for example, starting in January 1st of 2021 all the way to December 31st of 2024. So that'll be 4-year plan, 21, 22, 23, end of 24. That's a 4-year planning horizon. So think of these 01 as 2021 and 04 as 2024. So this becomes 21, 22, 23, 24. Sort of, this is what we're looking at. And at the start of each year, a decision has to be made whether I should keep the car or the cars or the fleet, because here we're looking at the fleet altogether, not a single car within the fleet. So you can think about the fleet as a single car or the whole fleet. So at the beginning of each year, I need to make a decision whether to keep the car or the fleet or replace it. Obviously, there are two conditions that at the beginning of the planning horizon, I have to buy the fleet or the car. So that means at the beginning I will have to buy, I will have to acquire, and then at the beginning of next year, if the constraints allow, for example here, minimum service of 1 year, so that's fine. So I can replace it within 1 year. So at the beginning of next year, I would make a decision whether to keep the fleet for an extra year or replace the fleet and get a new one. If I replace the fleet, I will obviously have to pay the difference. Okay, so I will give them old cars, they give me new cars, but I will pay the difference. And this is what I call the replacement cost. So here it says that if the car was acquired at the beginning of the planning horizon, which is 2021, then and replaced after 1 year, that means I replaced it at the beginning of 2022, or in this case 2002, then I will only pay $4,000. Okay, so if I keep the car that I acquired at the beginning of the planning horizon, I keep it for 2 years, then of course I'll pay more money because the cars are now 2 years older, so I will pay more money for replacement, and for 3 years I will pay $9,800 to replace the fleet. You cannot, that's why we don't have a 4th year here, because you cannot keep the cars in service for more than 3 years. Okay, so those are artificial constraints. They can change from one problem to the next. So obviously this problem says maximum service minimum service is 2 years, then that means I cannot replace, that means this doesn't exist anymore, because you cannot replace after 1 year, you have to keep them for 2 years. Okay, so but in this problem it's allowed to keep for 1 year only. So now the question is, what does this have to do with the shortest route problem? So basically I have to convert this table and this information into a network that looks like a shortest route network, and then solve it using Dijkstra algorithm. So each node in this network represents the beginning of the year. So node 1 represents the beginning of year 2001, and the node 2 the beginning of 2002, and until node 5, which is the beginning of 2005, which is the end of 2004. The connection or an arrow between node I and node J means I acquire in node I buy in node I, and I replace in node J. For example, here an arrow from node 1 to node 2 means that the cars were acquired at the beginning of 2001, or the fleet was acquired at the beginning of 2001 and then replaced at the beginning of 2002. So it's kept for 1 year, and thus the cost is $4,000, this number. Okay, while an arrow from node 1 to node 3 would mean that the fleet was acquired at the beginning of 2001 and replaced at the beginning of 2003, thus is kept for 2 years, and then the cost is $5,400. Okay, similarly, if an arrow from 1 to 4 would mean that you kept the car for 3 years and they pay $9,800. Okay, there's no arrow from 1 to 5 because you cannot keep the cars for more than 3 years, as the problem statement says in the previous slide. I also failed to mention in the previous slide that you have to sell or replace the fleet at the end of the planning horizon. So you have to buy, as I said, the car at the beginning of the planning horizon, but you also have to sell at the end of the planning horizon. In between, you can do anything you want in terms of replacement. So the other costs associated with this table would be an arrow from node 2 to node 3 would be 4,300 right here, and from node 2 to node 4 will be 6,200, and from node 2 to node 5 would be 8,700, and so on. Now, once we have developed the network for the problem, we can use Dijkstra to find the shortest route and then to find the answer for the replacement problem. The second problem that we're going to look at in this lecture is the network reliability problem, the most reliable network problem, and this is a slight deviation from the shortest route problem. Because instead of having the shortest route, I'm going to have the most reliable route. So imagine that you're just taking the freeway from city A to city B, and in the freeway there are maybe police patrols that can catch you speeding, or there are some speed radars that can also catch you if you speed. So and there's a probability that on the different routes connecting city A to city B, there is a different probability that you will be caught on various routes. You'll be caught speeding. So the question is, instead of taking the shortest route, I want to take the most reliable route, which minimizes the probability of being caught speeding in this connection. You know, you can think about it as also the most reliable route in terms of being caught speeding or making an accident due to, let's say, road conditions. So on these networks, instead of having the numbers on the arrows represent distances, now the numbers on the arrows will represent probability instead of distances. And the trick for converting those probabilities into numbers that I can work with using Dijkstra is to take the negative log, and that's natural log, I believe, negative log of the numbers on the arrows. For example, here 0.2 2 would represent the probability of being caught or making an accident, let's say, for driving from city 1 to city 2. Obviously, the question is, what's the most reliable route to go from city 1 to city 7? And the numbers on the arrows here represent probabilities of making an accident or being caught for speeding. For us to use Dijkstra, then I will convert these numbers, all the numbers, the probability numbers which are above or on the arrows, I will convert them to minus log. I'll take the minus log for all these numbers because these are numbers between 0 and 1, so the log of them will be always negative. So I take the negative minus log, so it will give us a positive number, and I end up with these numbers. Then I can actually use Dijkstra, which adds labels instead of multiplying them. And the trick is actually that if you take the log of P1 times P2 times P3, let's say these probabilities, then the log will be log P1 plus log P2 plus log P3, and thus I will be able to use Dijkstra. It's an algorithm that will add labels.